Welcome back. Let's try to make this a shorter video. The last one was a little bit long. So we're going to look at arcs and chords today. So we have some vocab here we need to go over first before we get to work. We have central angle, minor arc, and major arc. Now these all have to do with circles. So let's put a circle in here. First, a central angle. What a central angle is it's any angle that goes through the center of the circle. So let's say that's the center of our circle. If I have an angle like this, that would be a central angle because it is going through the center of our circle. All right. We could have all different size central angles. So with a central angle, we have a minor arc and a major arc. A minor arc is going to be this right here. So it's that distance along the circumference of the circle is my minor arc. Now my major arc is going to be the rest of it here. That is the major arc. All right. So the way that we measure arcs is in degrees, just like we did with angles. So let me make up a number here for my angle. Let's say this angle looks to be about 40 degrees. All right. So if my central angle is 40 degrees, the arc that it makes is going to be the same, 40 degrees. Now, my major arc then, some of you may already know this, there are 360 degrees all the way around. So my major arc is just going to be 360 minus that 40. So my major arc would be 320 degrees. So we have minor arcs, major arcs, and central angles. And the central angle is always going to be whatever degree it is. The minor arc is also going to have the same degree. All right. So here we have a theorem that we're going to have to put to use with some numbers and variables later. It says in a circle, congruent central angles have congruent chords and vice versa. So let's try and make an image of this. In a circle, congruent central angles. So if I make a central angle, let's say this is a central angle. That's a little bit big. Say this is a central angle. All right, and we'll say that is 50 degrees. All right, and this one is also 50 degrees. Looks a little bit smaller, but we'll just pretend it's the exact same. So those are congruent. In a circle, congruent central angles have congruent chords. So we have congruent central angles here. That means that they have congruent chords as well. So the chord of a central angle goes from one end to the other end in a straight line. So that chord is equal to that chord. They are the same. My drawing is not quite perfect, but I think you get the idea. If we have the exact same central angle, then the chord's going to be the same as well. So I drew another 50-degree angle somewhere in here. Let's say that's 50 degrees. We're getting sloppier. Then that chord is also going to be the same. And the same thing goes this vice versa here. If we have two chords that are the same, then that means that their central angles are also going to have to be the same. So it works forwards and backwards in this case. The converse works. All right, here is another theorem. In a circle, if a radius or diameter is perpendicular to a chord, then it bisects it. So let's try and make a picture and see what that looks like. We have a circle here, and we have a radius in the circle, right? So let's draw a radius. in a circle. If a radius is perpendicular to a chord, then it bisects it. So we need to draw a chord that's perpendicular to this, right? I'm going to use my straight line here for a chord. So if we make a chord going from one side to the other, it says if my radius is perpendicular to it. So if my radius and my chord are perpendicular, then the radius bisects the chord. It bisects it. What does bisect mean? It means it cuts it in half. So if my radius and chord are perpendicular, then the chord will be bisected. It does not work for the radius. Does not mean that the radius is also cut in half. That could be possible, but it's usually not going to be the case. But it will always be the case in regards to the chord. All right, let's look at a problem with that. So here we have a radius that is going right along there, and we have a chord that is perpendicular to it, right? So our theorem says that if we have a radius perpendicular to a chord, then it bisects it. So that means that this is equal to that, all right? So our goal here is to figure out what AB is, so this whole distance of that chord. I'm guessing since those are equal, we probably just have to find half of it, and we can double it by 2 there. So to find this, we're going to have to use this right angle and some right triangle knowledge that we've learned from previous classes. So if I draw this is a radius, right? The radius of this should be the same as that radius. So 5 plus 8 is 13. So I can find my missing side here with the Pythagorean theorem. A squared plus b squared is equal to c squared. It's like the hypotenuse is 13. We'll put it there. 5 and b squared. Alright, so 25 is equal to, or not equal to, 25 plus b squared is equal to 13 squared, which is 169. Now if I want to get b by itself, we subtract 25 on both sides. So subtract 25 and subtract 25. And on the right side, let's see, 169 minus 25. Throw that in the calculator. 144 is equal to b squared. Let's subtract 25 on both sides. Then to get b by itself, we need to take the square root, right? To get rid of that squared. So b will equal the square root of 144, and you can use your calculator if you don't know that it is 12. So that is 12, which means, this is also 12, which means my AB, it doesn't want to let me write up there, AB will equal 12 plus 12, or 24. Alright, that is it for today. I'll see you guys in class.